When gas and oil are produced together, the gas pressure after separation is often too low to meet the processing requirements of a large plant like this one. Gas pressure also needs to be at levels high enough for proper handling through pipeline sales facilities, gas lift, and injection purposes. So compressors are used to raise the gas pressure and meet these high pressure requirements.
This is the first section of a three-section module covering centrifugal compressor principles. In this first section, we'll find out why gas compression is important. We'll also look at the major parts of a typical centrifugal compressor and how it works. Then we'll introduce you to multi-stage and axial compressors.
Commonly, you'll find two main types of compressors in use today, the dynamic and positive displacement. Now, the most common positive displacement compressor is the reciprocating compressor, and the most common dynamic compressor is the centrifugal compressor. Every day, someone around us uses some kind of centrifugal compressor right in their own home. This hairdryer, for instance, is a type of centrifugal compressor with a heater. Even this vacuum cleaner is a type of centrifugal compressor. Now, in the oil field, the principle is basically the same, only the hardware is different. Centrifugal compressors we use are usually purchased as a compressor package. That is, they're made up of a compressor and several other components. So let's take a look at a typical compressor package.
A compressor package is made up of a compressor, a driver or power source, and often a gearbox. Couplings are used to connect the shafts of these major components. Also, you'll find that most centrifugal compressor packages include a seal oil system and a lube oil system. These can be identified by the maze of smaller piping surrounding the compressor package. Sometimes a gas cooling system is also part of the overall package.
Now that you've seen the major components of the compressor package, let's take a closer look at what these components do.
The compressor is the largest and most easily identifiable part of the entire package because of its large casing. This is where the internal parts of the compressor are housed, and it's also where the gas is compressed. Inside the casing are two special gas passages that form the stationary part of the compressor. These are the inlet guide and the diffuser, or discharge volute. The rotating part of the compressor is called the rotor assembly. The rotor assembly consists of a shaft and one or more impellers mounted on the shaft. As the rotor assembly rotates, each impeller delivers energy to the gas. The rotor assembly shaft is supported by bearings. The bearings prevent the forward and backward, or axial movement, and the side-to-side, or radial movement, of the shaft and impeller. A lube oil system provides the necessary lubrication to the bearings of the compressor. Often the same lube oil system will provide lubrication to the driver, gearbox, and couplings. Seals prevent the compressed gas from leaking out around the shaft. In addition to seals, most compressors have a seal oil system to further limit gas leakage. This seal oil system can either be a separate system or part of the lube oil system. The driver is the part of the compressor package that supplies the power to the compressor. It can be an electric motor, a steam turbine, or a gas turbine. A gearbox is often used between the driver and the compressor. This allows the compressor to run at a different speed than the driver. This gearbox may either be a part of the compressor casing or it might be in its own separate housing. The driver is connected to the compressor or gearbox through either a flexible diaphragm coupling or a gear coupling. The coupling allows for small misalignments between the two rotating shafts.
And that's a typical centrifugal compressor. Now let's take a closer look at compressor operation.
When gas enters the compressor, several forces are acting on the moving gas. One of these forces is aerodynamic. An aerodynamic force is the same force that causes an airplane wing to lift as it moves through the air. This lifting force helps to move the gas from low pressure at the eye of the impeller to high pressure at the outer edge. Another of these forces is centrifugal force. Centrifugal force is the same outward force children feel when they ride a merry-go-round. As they move away from the center of the ride, the children feel a much higher outward force that can throw them off the ride. Gas enters the compressor through the suction port and is directed to the center of the impeller. As the impeller rotates, the gas rotates with it. This circular motion generates the forces that lift and move the gas away from the center of the impeller, as well as creating a suction at the center of the impeller. Because the outside edge of the impeller travels faster than the center of the impeller, the gas is forced to increase its speed as it moves outward. The two forces, the lifting force and the centrifugal force, increase the motion energy or kinetic energy of the gas. As the gas leaves the outside edge of the impeller, it enters an area of the casing called a diffuser or volute. The diffuser is designed so that the flow area increases as the gas leaves the impeller. This increased area allows the gas to slow down or decrease in velocity. As the gas slows down, the motion energy is converted into increased pressure. Finally, when the gas leaves the compressor, the combination of all these forces, centrifugal force, aerodynamic force, and change in velocity, will have produced a gas discharge pressure that is several times higher than the suction pressure.
Well, as you can see, a centrifugal compressor involves several forces that increase the pressure of the gas. But what do you do if the discharge pressure still isn't high enough to meet processing requirements? How do we boost the pressure even higher? Well, typically in the oil field, we use a multi-stage centrifugal compressor.
In any typical centrifugal compressor, the force that's created by the impeller depends on three characteristics: impeller rotation speed, impeller diameter, and impeller shape.
Because each of these characteristics has practical limitations, there's also a limit on the maximum pressure only one impeller can produce. So generally speaking, the pressure produced by one impeller won't be enough to meet many oil field needs. This is why multi-stage centrifugal compressors are most often used.
Multi-stage centrifugal compressors are formed by joining several impellers together, each separated from the others by a diaphragm. Sometimes one impeller and one diaphragm define a stage. In other cases, however, a stage is defined from the beginning of a suction port to the end of a discharge port. In this case, the stage could have more than one impeller in it. In any case, the gas leaving one stage will always be at a lower pressure than when it leaves the next stage. In this way, pressure is increased in each stage until the final pressure is reached. In multi-stage compressors, the gas leaving an impeller of one stage flows through its diffuser and around a diaphragm. It's then directed by the inlet guide into the eye of the next impeller, where once again pressure is increased.
By now you should have a fairly good understanding of how centrifugal compressors do their job. But there's another type of compressor I want to briefly cover with you now. It's called the axial compressor.
Although the axial compressor is quite a bit different than the centrifugal compressor, it has similar applications, performance characteristics, auxiliary equipment, and even maintenance and operation procedures. In an axial compressor, the gas flow is along the axis of the shaft. Wing-shaped rotor blades attached to the shaft produce aerodynamic forces similar to the jet engine or to an airplane's propeller. As the blades of the compressor rotate, they cause the gas to move in a spiral or helical motion around the shaft. After the spiraling gas moves through one set of rotor blades, it passes through a set of stator blades. Stator blades are stationary and attached to the casing. They act in a similar way as a diffuser by decreasing the velocity of the spiraling gas and increasing its pressure. In this first section, we've seen how and why gas compression is important. We identified the major components of a typical centrifugal compressor and examined its operation in detail. You also saw how gas flows through multi-stage and axial compressors. Now, in our next section, we'll show you the centrifugal compressor in greater detail. Okay, take some time now to stop the videotape and think about what we've covered so far. Then fill in the blanks and answer the questions in your student manual. I'll see you when you're finished. Now, as you saw in the last section, the centrifugal compressor is made up of several components: the casing, the impeller, guide vanes, the diffuser or volute, diaphragms, bearings, and seals. In addition, most compressors also include a separate lube oil system, seal oil system, and a gas cooling system. In this section, we'll look at each of these in more detail. This is the second section of a three-section module covering centrifugal compressor principles. In this section, we'll examine the parts that make up the centrifugal compressor, and we'll look at its auxiliary systems. In centrifugal compressors, there are two primary casing designs: horizontally split, otherwise known as axial, and vertically split, or sometimes known as radial. This split in the casing provides a means for reaching the internal working components of the compressor for repair or replacement. In addition, the material used to make the casing is determined by factors such as stress, temperature, and corrosion. In the horizontally split casing, the split runs along the center line of the compressor. The main inlet and discharge nozzles, side connections, and other attachments are often built into the lower half of the casing. This allows the upper half of the casing to be removed for ready access to the compressor shaft, impellers, and bearings for internal inspection and maintenance. Horizontally split casings have split diaphragms, which can provide a potential leak path between stages. Also, at higher pressures, horizontally split casings are difficult to seal along the split line, so gaskets are used to seal against leaks. One final note about horizontally split casings. Because there's a possibility they might leak at higher pressures, they're seldom used above 400 psi. Now let's look at the vertically split casing. Vertically split casings are used in most single-stage and higher pressure multi-stage applications. The design of the vertical split reduces the wall thickness needed to confine the high pressure gas, and the smaller seams at the end plate allow for easier sealing. There are several vertically split configurations. One type consists of a cylinder with a removable end plate. When the end plate is removed, the shaft, impellers, and diffusers can slide out much like you'd take the batteries out of a flashlight. These working parts are often called the bundle. The bundle is horizontally split to allow installation or removal of the rotor as a unit. Another type of casing construction uses a vertically split outer casing or barrel and a stacked rotor and inner bundle. This is made up of several donut-shaped parts with vertical joints that form the passageways and the bundle itself. Assembling and disassembling the casing requires a piece-by-piece assembling and disassembling of the rotor as well. Now that we've seen the outside of the compressor, let's take a closer look at the internal components. Inside the casing is the rotor. Rotors usually consist of a solid center shaft with impellers keyed and pressed onto the center shaft. In most centrifugal compressors, rotors are built with a balanced piston installed at the discharge end to relieve the thrust-bearing load. stacked rotors consist of a stub shaft for each end, several impellers, a balancing piston, spool pieces, and other needed parts, all held together with a heavy center bolt. Although this type of rotor is always used in a stacked style, vertically split casing, it can also be used in other types of casings as well. The impeller is the most critical part of a centrifugal compressor because its size, shape, and speed determine the compressor performance. Most often you'll find two types of impellers, closed and semi-open. In a closed impeller, shrouds cover both sides of the blades. On one side, a central hole or eye allows gas to enter the impeller. The closed impellers are the most common and are mainly used in multi-stage compressors. In the semi-open impeller, a shroud completely covers and forms a solid backing for one side of the blades. Semi-open impellers are used for large gas flows and are generally used only on single-stage compressors. The blades, or vanes, on an impeller can be straight, curved forward, or curved backward. Backward curved vanes are the most efficient and stable. However, since backward curved vanes cause the gas to leave the impeller with less velocity, there is less velocity to convert to pressure. Most oil-field centrifugal compressors use the backward curved vane impeller. The balancing piston is fixed to and rotates with the shaft. It is surrounded by a seal that minimizes leakage from the upstream side of the shaft to the downstream side. The downstream side of the balancing piston is piped back to the compressor's suction side through a balancing piston leak-off line. This causes a pressure difference across the piston that provides a net thrust on the shaft to compensate for the thrust being exerted on the impellers. Near the inlet and between stages of the compressor are guide vanes. They're used to direct the flow of gas into the eye of the impeller at just the right angle. This is important because efficient performance and stable operation of the compressor depends on the velocity and direction of the gas entering the impeller eye. Guide vanes can either be fixed or adjustable. Adjustable guide vanes are usually available on single-stage compressors and are sometimes used in the first stage of multi-stage compressors. These vanes can either be adjusted manually or automatically to control the angle of the gas flowing into the eye of the impeller to keep it running stable and efficient over a wider operating range. As the gas leaves the impeller, it's forced into a passageway in the casing called the diffuser. The diffuser forms an increasingly larger path for the gas to flow through. Now let's look at how each stage in a multi-stage centrifugal compressor is separated from the next. All the parts that make up one stage of a multi-stage centrifugal compressor can be found on a single-stage compressor. One stage is separated from the next by a specially designed part of the casing called the diaphragm. The adjacent walls of individual diaphragms form a diffuser passage. After the gas travels through the diffuser, it passes through the return channel of the diaphragm. Diaphragms can be horizontally split or fully circular. In large horizontally split compressors, the heat from gas compression can cause the case to expand, which in turn expands the diaphragms. If this happens, lower gas pressure and leaks could result. Sometimes this problem is corrected by circulating cooling water through the channel. In stacked casing designs, the diaphragms are one piece and therefore provide greater stability and strength. In addition, the one-piece design eliminates interstage leaks and helps contribute to higher efficiency. Most compressors need some type of sealing to keep the compressed gas from leaking out of the compressor and to prevent leaking between stages. Particular care must be taken when the gas is combustible. That's one reason why seals are so important. Let's examine some of the types used. The most common types of seals are the labyrinth, liquid film, carbon ring, and mechanical. The simplest type of seal is the labyrinth seal. It has a series of grooves machined to sharp knife-edge thickness that maintain a close clearance to the mating part. It can either be stationary or rotating. The mating parts are made of a softer material such as babbitt, so they will wear before the labyrinth does. Labyrinth seals can be found in multiple, stepped, and interlocking configurations. Sometimes carbon rings are included with the labyrinth seal. On high pressure and heavy duty compressors, liquid film seals are the most common. A typical seal consists of 2 or more rings that don't rotate but are free to float with shaft movement. Oil is injected between the rings at a pressure higher than the compressor suction pressure. This allows the oil to flow between the seal rings and the shaft and then into the oil drains. Labyrinth seals guard against any oil leakage into the gas stream. Emission regulations sometimes require the use of liquid film seals. These seals provide a barrier fluid which prevents leakage of processed gas to the atmosphere. Carbon rings, on the other hand, are dry contact seals, which consist of several high-quality carbon rings held in place by stainless steel spacers and axial springs. The entire seal assembly can be removed from the compressor when worn or broken segments need replacing. In some applications, a buffer gas is used in conjunction with the carbon rings to separate the gas in the compressor from the surrounding atmosphere. Also, you'll find combinations of carbon rings and labyrinth seals are also used. Another type of seal is the mechanical contact seal. It consists of machine rotating and stationary surfaces that remain in direct contact with one another to prevent leakage. Mechanical contact seals are primarily used for low-pressure gas that has no corrosion components. One typical form of the seal uses a rotating contact ring, a full floating carbon wear ring, a stationary mating ring, and a spring-loading device. A small quantity of lubricating oil is used to remove frictional heat. This type of seal provides some sealing whenever the compressor is shut down. Not only do we have to seal against leaks, but we have to guard against any unwanted movements of the shaft as well. And that's where bearings play an important part. Inside the centrifugal compressor are forces that tend to cause the shaft to move in a forward and backward direction, commonly referred to as axial motion, and a side-to-side direction, commonly referred to as radial motion. For example, an unbalanced impeller can cause radial motion. Self-aligning tilting pad bearings are used to support the shaft and prevent radial and axial motion. In most large centrifugal compressors, a tilting pad journal bearing is used. This type of bearing is designed to prevent the rotor oscillations associated with the standard sleeve-type journal bearing. As the shaft rotates, a wedge-shaped film of oil produces a stabilizing force that tends to reduce vibration. This self-aligning property will compensate for any misalignment and will tend to distribute the loads evenly. To control the axial motion of the shaft, thrust bearings are used. They are usually of the double-acting tilt pad design, so that thrust loading in either direction can be supported. A typical thrust bearing has a thrust collar attached to the shaft and thrust shoes arranged in a circular bearing case. Between the thrust collar and thrust shoes, an oil film is used to support the thrust load. Almost any large machine needs some type of lubrication, and the centrifugal compressor is no exception. Without the proper lubrication, frictional heat could build up to a dangerous level, possibly damaging the compressor. That's why lubrication systems are so important. Most centrifugal compressors use external lube oil circulation systems to lubricate and cool all bearings and gears in the compressor and accessory drivers. A typical lubrication system consists of an oil reservoir, an oil pump, a filter, and a cooler. Inside the reservoir, special baffles are built in to prevent the oil from foaming. Now here's how the lube oil system works. Oil is pumped from the reservoir through a filter to a cooler, where it is cooled to the correct operating temperature. This cooled, clean oil then flows under pressure to each bearing through holes and grooves. Gravity allows the oil to make its way back into the oil reservoir, where the cycle starts all over again. Most lube oil systems also have an auxiliary pump and dual filters. These help give added protection to the lube oil system. Now let's look at another circulating oil system, the seal oil system. Oil film seals are used on many compressors to positively seal the production gas inside the casing. In some situations, a separate seal oil system is used. However, in most cases, a combination lube oil and seal oil system is used. Sometimes a buffer gas system might be used along with the lube oil and seal oil system, if necessary. Seal oil enters the space between the seal rings from an overhead seal oil tank. Oil which has been used only for lubrication drains back to the reservoir. Seal oil which may have come in contact with gas drains into drain pots for removal of the gas. The separated oil is then returned to the reservoir for recirculation. One thing you should always remember about lube and seal oil systems: always make sure that any oil removed from the sumps or reservoirs is disposed of using approved methods. All right, you've seen how the lube oil system helps lubricate the working parts of the compressor and in turn reduces heat from friction. Now let's look at how we reduce the heat in the gas we compress. Heat is generated when gas is compressed. That's why for safe and efficient operation of the facility, the compressed gas must be cooled. Also, high gas temperatures make it difficult to lubricate the bearings and other moving parts. This is particularly true if the gas is to be recycled through the compressor, because hot suction gas will overheat the compressor and cause serious damage. In many large compressors, the gas flow is changed from the typical straight-through arrangement. The gas is actually taken out of the compressor at an intermediate pressure and circulated through a heat exchanger called an intercooler. Here, the gas is cooled before it is returned to the compressor at another point. On very large multi-stage compressors, there may be several intercoolers. Even with intercooling, discharge gas may still be too hot for delivery. In these cases, the discharge gas is passed through a heat exchanger or aftercooler before it's delivered to the pipeline. In this section, we've shown you in detail all the parts that make up the compressor and what they do. And we've taken a brief look at its auxiliary systems. In our next section, we'll be getting familiar with drivers, couplings, and controls. But first, stop the videotape and take some time to review your student manual and answer the questions at the end of this section. I'll see you when you're finished. An airplane's propeller does is only as good as the engine that turns it, because without a propeller, the airplane wouldn't fly. Well, the same thing could be said for the work a compressor does and the drive unit that runs it. Without being coupled to a drive unit, the centrifugal compressor wouldn't move 1 cubic inch of gas. This is the third section of a 3-section module covering centrifugal compressor principles. In this section, we'll look at various drivers and methods of coupling them to the compressors. We'll also see how flow is controlled to produce the correct gas pressure. Centrifugal compressors are available over a fairly wide range of speeds, anywhere from 3,000 RPM on up to as high as 50,000 RPM. Therefore, the type of power unit used depends on the desired speed range, loading of the compressor, and available fuel sources. In higher speed and load applications, the steam or gas turbine
is the most commonly used. Now, in low-speed or small-load compressors, electric motors are sometimes used. Let's take a closer look at these different drivers. In steam or combustion gas turbines, speed-increasing gears are often needed between the turbines and the compressor shaft and are connected with couplings. Commonly, steam and gas turbines use speed-increasing gears between the turbine and the compressor. Steam and gas turbines generally rotate at high speeds and therefore can sometimes be used to drive high-speed centrifugal compressors without any gearbox. This is known as direct drive. Turbines are also variable speed drivers that use governors to keep their speed constant and control the amount of steam or gas that's supplied to the turbine during operation. Turbine speed is measured by a control mechanism that actuates a throttle valve to increase or decrease the supply of steam or gas to the turbine. In compressors driven by electric motors, speed is generally limited to around 3,600 RPM. In these cases, the electric motor may be coupled directly to a low-speed centrifugal compressor. To operate the centrifugal compressor at higher speeds, the motor must be coupled through a speed-increasing gearbox. This is known as a gear drive. The gear drive and coupling configuration is often used in the oil and gas industry. Gearboxes can either be an integral part of compressor construction, or they can be external auxiliary equipment connected between the driver and the compressor. Almost all compressor driver applications use some sort of coupling. Couplings are used to transmit motion between two shafts that are almost but not quite in perfect alignment. They must also be able to withstand changes in compressor load or stoppage of the driver altogether. Now, there are two types of couplings commonly used to connect the driver to the centrifugal compressor: the gear coupling and the flexible diaphragm coupling. Gear couplings are widely used in high-speed, high-load compressors. They work by allowing their parts to slide or otherwise move relative to one another, with no deliberate bending or flexing. External teeth on the hub of the coupling are free to rock back and forth or move axially within the internal teeth of the sleeve. Small couplings are sometimes grease-packed. Large, high-speed couplings use circulated lube oil. The flexible diaphragm coupling is commonly used with turbine-driven compressors, where distortion due to heat is substantial. The flexible diaphragm coupling transmits power from the driver to the compressor using a solid, rigid hub on each unit. A flexible metal diaphragm is bolted to the outer rim of each hub, and a spacer connects the two diaphragms. All misalignment is handled by the elastic flexing of these thin web diaphragms, and there is no rubbing movement of any parts of the coupling, and no lubrication is required. These couplings can handle fairly large angles of misalignment between shafts. However, this coupling can tolerate only slight changes in back and forth movement of shafts. There are several factors that affect performance of the compressor. For example, varying the speed of the compressor will vary the volume of gas moving through it. Recycling gas back to the suction side will also alter the performance characteristics of the compressor. So in this way, operators can achieve different results for the compressor. To control performance in some compressors, adjustable guide vanes are installed just ahead of the impeller. These guide vanes slightly throttle the suction gas flow and pre-rotate the gas into the impeller eye. These guide vanes can either be adjusted manually or adjusted automatically with a suction pressure controller. One problem in dealing with gas flow through a centrifugal compressor is surging. Surging is a rapid flow of gas back and forth within the compressor. It is an aerodynamic condition caused by a recirculation of the gas starting near the edge of the impeller. This is similar to the effect of swirling airflow on top of an airplane wing that breaks the lift of the wing and causes a stall. With an airplane, this happens when the pilot attempts to gain too much lift at too low a speed. In a centrifugal compressor,
This happens when the compressor attempts to raise pressure too quickly at a flow rate that is too slow. At a given RPM, a decrease in flow rate normally will cause an increase in pressure. However, as the flow rate becomes too small, the gas will separate from the vane tip. As a result, that vane passage loses the ability to increase the gas pressure. When that happens, there will be a slight amount of backflow from the diffuser until lift is regained. If the flow through the compressor is decreased even more, a point will be reached where there's a complete recirculation of flow through all vane passages of the impeller. This causes a large amount of backflow and a violent surge can occur. In addition, these large flow reversals can create loud noises, thrust fluctuations, and damaging vibrations in the compressor. While surge is occurring, the gas is recirculated through the compressor and becomes heated by the compression process. As the gas recirculates back to the impeller into lower pressure, it retains that heat. As it is recompressed to its original high pressure, additional heating takes place. If this is allowed to continue unchecked, the gas will become hot enough to cause a bearing or seal failure. A thrust bearing failure can be caused by thrust reversals that occur from the rapid and violent recirculation of the gas. Sometimes these thrust reversals are so violent they can exceed the load capability of the thrust bearing, causing it to fail. This combination of thrust bearing failure and overheating can be catastrophic to the centrifugal compressor. So, some kind of protection must be used to prevent this from happening. That's why you'll find most compressors use a surge detection system. The surge detection system senses discharge pressure variations and initiates a compressor shutdown in the event of a potentially serious condition. A surge control system can also be installed that allows discharge gas to be recirculated outside the compressor to the suction side. The objective here is to keep the flow above the surge point. An anti-surge control valve in the recycle line is regulated with a flow controller that senses the rate of the gas flowing into the compressor. If the flow rate is less than the set point, the valve opens and allows enough recycled gas to enter the suction port to keep the compressor flow rate above the surge point. In addition to anti-surge protection systems, other safety devices are commonly installed on centrifugal compressors and their auxiliary systems. Drivers, for example, must have their own protection devices to prevent them from being damaged by overload conditions. Electric motors are protected from overloads and overheating by thermostats and circuit breakers. Turbines are protected from overspeed damage by governors and overspeed trips. In the different types of compressor bearings, temperature sensors are frequently used to monitor startup and operating temperatures. Vibration monitors are placed at strategic points on the compressor to check for any excessive vibration. Some of them are designed to specifically monitor excessive axial or radial movement of the compressor. Vibration monitors are also connected to control systems that will sound alarms and shut down the equipment if necessary to protect the compressors from serious damage. All right. Now in this section, we've looked at the various drivers and the methods of coupling them to the compressor. We've also seen how the flow of gas is controlled to produce the pressure needed for proper processing and handling. And finally, we showed you some of the safety features the compressor and its auxiliary systems use. Well, that wraps up this module on centrifugal compressor principles. By now, you should have a fairly good understanding how centrifugal compressors do the job of compressing gas and how they're configured for use in the oil and gas industry. Take some time and think about everything we've covered. Then answer the questions in your student manual. If you have any questions, play the tape again or ask your instructor. See you next time.